full screen. Does it full screen or not?
It's great. Yes,
Yes.
that's great.
Okay, perfect. Yeah, thanks so much for inviting me. Excited to share some of our recent works on instruction following and evaluation using LLMs. So I chose this topic because first it's like an important topic, and then it doesn't require too much like technical background to understand what the talk is about, and my goal is to basically tell you a little bit about challenges of using LLMs for evaluation and how we can kind of overcome them. So yeah, and if you have questions, please feel free to interrupt me and ask. I prefer this to be kind of interactive. Cool. So this is like the talk is about instruction following, and then you might ask, what is actually instruction following? So instruction following is actually can be viewed as an API of a language model for humans to use them. So you have this human, and then basically they issue some instructions to the model, and then the model provides some response. And this instruction following is generally an umbrella term, which includes a lot of different tasks. This could be, for example, generation, open domain QA, chat, writing, summarization, and so on. So if you look at some of the benchmarks that people use to evaluate instruction following, it includes a lot of different tasks, including, again, like reasoning, math, coding, writing, etc. And usually the instructions, I think all of you have like interacted with ChatGPT or LLMs, and you know that like you provide the instruction to the model and it provides a response. So in order to train the models, just to give you a little background on like how these models are trained, in order to train models to do instruction following, usually people do like a first stage of like fine-tuning models on these responses. So the training data includes the instruction and the reference response. And then the model is fine-tuned to generate this response given the instruction. And this is also referred to as like SFT or supervised fine-tuning. And then there is like the preference optimization methods that people use to kind of fine-tune models to provide better outputs. And in this setup, basically you have pairs of responses. So given an instruction, you have like a winning response and a losing response. And you train the model so that it kind of has a higher probability to output the winning response rather than the losing response. And this is like a famous methods for this are like RLHF, PPO, DPO, and models in that family. So I want to first focus on text summarization as an instance of instruction following that is like a task that requires the models to like read the input articles and like give an additional instruction, for example, like summarize this article in 3 sentences or summarize the main points about this a certain topic. We want to generate an output. And summarization is a classic NLP task. Like people have been working on this for past 20 plus years. And there's been a lot of progress on this. So I want to tell you a little bit about this and how actually this changed since LLMs came about. So it turns out that like several studies are showing that like LLMs are highly capable zero-shot summarizers. So if you have like smaller supervised summarization models, these are models that are trained on summarization tasks. And if you compare these with like generic or general like LLMs, it turns out that LLMs perform better. So here in this graph, like I'm showing 2 models that are small models like Brio and T0. And then comparing these with GPT-3, this work was done around the time that GPT-3 came out. So you can see that most of the time, the human annotators are preferring the GPT outputs, although Brio and T0 are explicitly trained for summarization. So here, the more green means that the more preference towards that system compared with other systems. There's another work showing similar results that like GPT-3 model can actually achieve higher preferences compared with smaller task-specific models. And there's other work that show that, okay, if you look at tasks like news summarization, even like models like ChatGPT are kind of comparable with freelance writers. Like you don't see huge difference and it kind of is subjective. So based on this, it looks like LLMs are actually a very good summarizers. And finally, this is the last slide about the like prior work. And this shows, like, if you look at each cell, for example, this one, it's like this one, it shows the like the win rate of this system with respect to this system. So if you look at the last column of each of these like tables, you see that like GPT-4 is actually able to win against human written summaries. And this is the case for most of these data sets. So we wanted to then look into this in more detail and see, okay, like what are the main properties of summarization, and can we actually improve the performance of smaller models on summarization? Because it's not very intuitive that like you have a very task-specific model that is trained for that task, but still there's such big gap. So this was a paper that was published earlier this year. To give you a little bit background, usually like LLM generated summaries can outperform reference summaries. And then you might ask, like, what are these reference summaries? These are summaries that are like the gold standard summaries in summarization data sets. And how they are created is actually, they are scraped from websites like CNN's or like Daily Mail and so on. So this is an example article that I just took today. And like a lot of famous summarization data sets are like this, that they take the highlight of the article here as the summary, and then they take the article as the document that you want to summarize. However, these bullet points or these highlights actually do not necessarily reflect the article's content. Some of them just provide some highlights that is more for like kind of the main news is there and the article provides just additional context. So if you train a model that given this article generates this reference, it probably won't work very well, or it won't be like a good general summarizer. So given this question, we wanted to see what happens if you train a small models on better summaries, like not training it on like web scrape summaries, but actually higher quality summaries. Do we still see large differences? And then we wanted to investigate this using additional training, because as I mentioned before, LLMs are going through two stages of fine-tuning or post-training. One of them is this preference optimization. And the smaller models do not have that. So the main question is like, what happens if we use better summaries and better training objectives? And again, like just as a background, the baseline training method, it's referred to as maximum likelihood estimation, that you basically train the model to maximize the probability of the reference summary given the article. And then you can also train the model in a contrastive learning setting. For example, we took the BRIO method, which trains the model to assign higher probability to the better summary. So the second one is like a contrastive learning setting or a pairwise setting, whereas the first one is just a standard fine-tuning. And using this, we train a small model, which is BART, and this is like a 700 million parameter model. So it's very small, like, and just to compare, GPT-3 is like 300 billion parameters. So this is orders of magnitude smaller. And for the reference, again, like we use the LLM generated summaries instead of like taking the summaries from this data set. So simply we ask the model to summarize the article, and then we use this for training. And then for the pairwise setting, we ask the model to generate two summaries, and then we rank them, and we ask the LLM to say which one is better, basically. And then, yeah, for evaluation, we use LLM-based evaluation that I'm going to talk more about in the next section. But here is just like you prompt like a model like GPT-4 to say which of these summaries are better. And so first thing is like people have looked at this LLM-based evaluation. There are methods like GPT score that given a prompt and an output, it produces like a score or the probability of this summary. And the higher probability means that that summary is probably better. And for the like the pairwise setting, there's GPT rank, which basically ranks the summaries and say which one is better. And we consider two different training settings. The first one is like low resource, where you use an expensive but higher quality model. For example, at the time it was GPT 3.5 and GPT-4. So we generated only 200 examples of GPT-4 and like 10,000 examples GPT 3.5. And then the high resource setting is like inexpensive. You can use an open source model like Llama and a small version of it, and then generate a lot of training data, like 200,000. And then we perform both of the training objectives, both MLE and the contrastive learning. So the first experiment we did, it was using GPT score as evaluator, and we compared the BART model, like this one, which is like the original BART, with GPT-3. And we can here see that like the performance is much worse compared with GPT. However, like when we do our training, like just training using the like LLM generators summaries, we see like a large improvement in terms of the GPT score performance. And then we also looked at the contrastive learning. So the second one is like a contrastive learning objective. And here we see that the contrastive learning actually helps further improve the performance. And then here are like experiments with the GPT rank, which again like ranks two summaries and says which one is better compared with the other. So here are the win rates against GPT 3.5. Yeah, this is the original BART model. You can see that it barely wins anything. It almost always loses or ties versus GPT 3.5. And then these are other models that are a bit older than GPT 3.5. So our first setup, just using MLE, we can see that like we can shift the performance of BART quite a bit higher. And then now we have 14% win rate against GPT 3.5. And then with the contrastive setup, we can even push this higher to 31%, which means that it's kind of on par with GPT 3.5. And then the next question is like, here we generated the summaries using GPT 3.5 and use them for training our models. What happens if you use even a stronger model to generate these summaries? And we see that, okay, if you use a stronger model to generate summaries, you even can outperform the previous results, yeah, more. However, this was an encouraging result, but it was a little too good for us to believe, because like this is a still very small model, like 700 million parameters, and we didn't expect it to really outperform GPT 3.5. So we thought maybe there is an issue with the evaluation, because this uses GPT 3.5 as evaluator. So when we switched the evaluator to be GPT-4, which was a stronger model, we no longer see that type of like improvement over GPT 3.5. It is still improves quite significantly compared with the original BART model that you see on top, but it's still like there's a gap with GPT 3.5. And then, according to GPT-based evals, so far we've seen that we can close the gap of small models with a little bit of extra fine-tuning on LLM-based instructions. The next question we wanted to ask is like, okay, the LLM summaries are small, like we had only 10,000 examples. What if we have a lot of data? It might be like lower quality, but because it's cheap, we can just generate a lot of data. So we use an open source model, Llama 2 at the time, to generate a lot of summaries, and then train this BART model. And the Llama model is much smaller than GPT, but it's still 10 times larger than our model, and it's heavily trained. So we expect it to still provide good signals for our model. So we generated like 200,000 summaries using Llama 2 7B. And then for the pairwise setting, we used the auto ACU setting, which is like an evaluation framework that creates atomic content units and checks the quality of the candidate summary with respect to these atomic units. And then it basically says if summary A is better than summary B. And then we use this as the pairwise training data. So next, using this, we were able to actually further improve the performance, and we actually were able to outperform GPT 3.5 under GPT-4's evaluation. And this was a very encouraging result that, like, yes, using a lot of training data, you can actually distill into a smaller model and get high performance. So, but again, like our question was, is this really the case? Is this really the case that the smaller models fine-tuned on a specific task are better than LLMs? According to LLM-based evaluations, it seems to be the case. But we needed to investigate this further. So we did human evaluation, because like using LLMs as evaluators may not always be reliable. So we asked human annotators to go through these generations and then like evaluate the quality of the summaries in terms of salience, coherence, and overall quality. We noticed that it's very difficult to achieve high agreements among crowdsourced annotators because like the quality of the summaries were kind of close, because we were comparing models that all produce like plausible sounding summaries. The differences were nuanced. So we needed to use like in-house annotators that are familiar with the task, are trained to perform this type of evaluations. And here we see that, okay, there is still a gap with GPT 3.5. We still see like large improvements compared with BART. Like here, for example, BART means like only 10 cases, but like our model gets like about 29 cases in terms of like salience, and the overall score is closer. So while we still can close the gap, it's not like we are outperforming GPT 3.5. And then in the high resource setting, we are seeing that the model actually kind of performs on par with the low resource setting. However, like the contrastive learning is actually much better. So the next question is like, now that you have both the human evaluations and the LLM-based evaluations, in this type of like instruction following summarization, are LLMs reliable evaluators? So we looked at basically the correlations, and we saw that like although in our case like Brio Llama 2 wins over ChatGPT, it's not the case with human evals. So there are some discrepancy here. And we measured the agreement between the LLMs and the humans on instance level. So for each instance, we look at the outputs and see which one the LLM agrees with human and which one it doesn't. So these are like Clippenter's alpha numbers. We see that like for individual crowdsourced annotators, actually GPT-4 has better correlation. However, like if you use like majority voting, still like the crowdsourced annotators are better than GPT-4. So the lesson here is like, if you want to like use crowdsourced annotators, we are seeing that like the average crowdsourced annotator like is probably you can just use GPT-4, and now we have like GPT-4o, which is even better. So for this type of task, it looks like individual crowdsourced annotators are not that good. And then we also noticed some biases in terms of like these evaluations. Like most of the time, these models prefer the second output. So if you put two of the systems in the prompt, and then it usually tends to select the second one. And you can see up to like 50% inconsistency in terms of like if you swap the output, it changes its evaluation. And this is something that like other people have also noticed. Sorry, was there a question? Okay.
Actually, a question I didn't ask it before, but how many annotators do you have there?
I think it was 4 annotators.
4?
Yes, 4 annotators.
So did anybody try to take 4 different LLMs and use them as fake annotators and combine them and see what their majority voting does?
Yeah, that's a good question. We didn't do that in this work, but in the next work that I'm going to present, we did that actually. Yeah. Cool. So the point is, the point of this work that we wanted to show was domain-specific LLM distillation actually works. Like you can use LLMs as gold standard and then basically train very small models that can do constrained tasks very well. And there's 2 key points here. Like first is like the amount of training data matters, and the training objective also matters. Like if you just use the regular SFT, you won't get close performance, but you need to use the contrastive learning training to be able to close the gap with larger models. And the next lesson was that like LLMs are not robust evaluators, and somehow we can say that these smaller LLMs can overfit to LLMs evaluation. So if LLMs have some tendency to prefer one output versus the other, you can train a smaller LLM to mimic that behavior. And that like human evaluations might be still.
Currently, do you want your vitamins?
Sorry?
Oh. I apologize.
Oh, no problem. Okay. So this brings me, maybe this is a good segment to go to the next part. That is like specifically focused on evaluation of instruction following. So why this is important? Because like right now, all of the model developers are kind of competing for these type of leaderboards that evaluate instruction following capabilities of models. For example, one of them is Chatbot Arena, that is kind of like a gold standard. This is like an open interface that anyone can access. You can provide your own prompt, and then you are presented with two outputs. For example, here your prompt is how many R's are in word strawberry. And then you are presented with two outputs from two models that you don't know which is which. And then you select, for example, one of these. And then it reveals the like the underlying model. And these user preferences, these are like human judgments, are stored and used to kind of come up with this type of rankings. And you can see that, for example, on this type of leaderboards on Chatbot Arena, ChatGPT 4.0 is on top, and then like models like Grok and like I don't know Claude are next, and so on. And this gets updated quite frequently. And then why this is important, evaluation can be also used to guide training of these models, because you can like use this type of evaluators as reward models to provide reward for your reinforcement learning objective, or reinforcement learning with AI feedback objective, that you use these evaluators to tell you which output is better, then fine-tune the model to encourage it to generate this type of outputs. And then another type of evaluation is like, we saw that the chatbot arena is kind of a crowdsourced evaluation, that you provide a large number of prompts by users, and then they identify their preferences. However, like if there is like budget, some people also do expert or trained annotations. For example, I took this from the OpenAI website, that they compared their recent model O1 preview with GPT-4 using like expert annotators. And on some tasks like mathematical calculations, they see like huge performance improvement, whereas tasks like writing, they don't see as much improvement. And then the question is like, human evaluation is good, but it's very difficult, it's expensive, and there's a lot of noise, especially if you're dealing with crowdsourced annotations, and it's not reproducible. Based on this, people have been using LLM as judge or like LLM as evaluators, where you provide a prompt saying that, hey, model, you are an evaluator or you are a judge to decide which one of these outputs are better. Please tell me which one is better. And then model produces an output. And based on this, actually, people have created other benchmarks like Alpaca eval. Here, they compare the output of any model versus a baseline, which is GPT-4, and then they use GPT-4 as the annotator or the evaluator. And then they rank models based on this. Whoever wins more against GPT-4 actually ranks higher. And then there's benchmarks like Arena Hard, which took 500 challenging user queries from Chatbot Arena, and then they prompt GPT-4 as judge to compare models against a baseline. So it's kind of similar setup. So if you see this type of leaderboards and you wonder how are these working, it's based on this basically. Either you have human eval based on Chatbot Arena, or you have auto eval based on some model-based evaluations. And the last one is Wild Bench, which uses a more diverse set of prompts, but it has the same kind of concept. So in this work that we recently put on arXiv, basically we wanted to visit instruction following evaluation in more detail and see what are the effects of different protocols and different models. So yeah, here there are two types of evaluations. If you want to compare how good an evaluator is, one way is to use that evaluator to get a system ranking and then compare that ranking with Chatbot Arena, which is like user-provided rankings. And whatever evaluator gets better scores, it's deemed better. And then there's instance level, where you kind of like compute the agreement or like the accuracy of LLM judgments with respect to human judgments. And LLM evaluators have a lot of biases. As I mentioned, for example, that they could have positional biases. This work shows that, like, usually, like, for example, if you're comparing these two models, usually the model prefers the first one and so on. And then sometimes the models prefer their own output. For example, if you use GPT-4, it tends to select GPT-4 generated output versus others. There is also a significant issue with length bias. A lot of models, if you use them as evaluators, they tend to prefer longer output versus shorter output. So our approach is like performing a larger scale instance level meta evaluation to have a better insight on like which LLMs are better and which evaluation protocol is better. So there's a lot of like LLMs that people have released, and there's also reward models that people use to train models. There's fine-tuned models and so on that people specifically fine-tuned to do better judgments. And there are like evaluation protocols or prompting protocols, or as Yuval mentioned, basically you could have a majority voting protocol. So these are things like self-reference, GPT-4 as reference, and so on. So we looked into a lot of these evaluation protocols as well. So basically, as I mentioned, there are two dimensions. One is the base LLMs that you use, and the second one is the evaluation protocols. And the important thing is, like, unlike prior work, we scaled up the number of base language models and the evaluation protocols. Because there's a lot of like variance, it's usually helpful to increase the number of data points so you can have like a better confidence in the results. So we looked at 4 evaluation data sets, 25 open source LLMs, and 15 evaluation protocols. So the data sets we considered are like LLM bar, which basically like present 2 different outputs to users and then ask them to say which one is better. And then we also considered this instru-sum dataset, which is instruction following summarization, that you ask the model to generate a summary with respect to some topic. So we chose this data set because we wanted to have high quality data sets with high human agreements. And you can see here the agreements between human on these data sets, which ranges between 80% to 100%. And then we evaluated 2 things. The first one is just evaluation accuracy with respect to human, and then self-agreement, like if you swap the output, like how many times the LLMs agree with themselves. So here's like the overall results. You can see here, like I know there's lots of numbers and lots of models listed, but basically this shows base models like GPT-4, GPT-01, and so on. And like if you look at the average final numbers, you can see that like GPT-4 models are very good and they're on top. However, the open source models like Llama 405B and Llama 70B actually have very high performance, and the gap is not that big, which is encouraging. We also looked into reward models, which is this yellow rows, and also fine-tuned models. You can see that in general, like the Llama models are good, and the reward models are good, but do not outperform the general like Llama models. And the fine-tuned models can actually outperform their base models. Like here, like this model, the offset bias is fine-tuned version of Llama 3, and it seems like it can outperform it quite a bit. So yeah, the other thing was we looked into the evaluation protocols that people used in other benchmarks. For example, in Arena Hard, Wild Bench, or Alpaca Eval, people use more complex prompts. For example, they use finer grain prompts, tell the model like in terms of salience, which output is better, in terms of like coherence, which one is better, and so on. And we find that actually those type of prompts don't work quite well here. And you can just use a simple like baseline prompt that asks the model, like just compare the two outputs and say which one is better. So this is the first thing, that like a straightforward prompt usually works better than more complex evaluation protocol that was used in other benchmarks. Now we look into the evaluation protocol that are more complex. And so in this analysis, we have like a big grid of models and evaluation protocols. Here we are looking at evaluation protocol performance averaged over all models to see which protocol is better. And so far we see like prepare protocol is better. And prepare is like this. You are comparing two outputs, A and B, and then instead of asking the model to just do a pairwise decision, you ask it to first argue which one is, like argue about them individually. For example, here it says A is good because of this, and B is bad because of this. And then finally, it produces an output. And this was a protocol that was kind of introduced by a prior work. And it means that like basically it is better to generate a rationale and then the pairwise decision across different models. And then the next protocol that was performing well was the GPT-4 as reference. This is also an interesting protocol where like if you have two outputs that you're comparing, first you ask the same prompt to GPT-4 to give you an answer, like by ignoring the two outputs. And then you compare the output that GPT-4 generates with each of these systems. And then the model selects, for example, one output. And it seems like this reference-based evaluation is actually quite helpful. And then the next question was the self-consistency. Like, again, just to remind you, the self-consistency is like if you swap the output order, does the model prediction change? And we can see that across all the different protocols, this actually is a problem. But one of the protocols that like is called swap and synthesize actually solves this problem. And if you look at this protocol, it's very expected because like you swap the outputs, you ask the model to generate an output, and then you ask the model now based on these two, like reconcile the conflicting reasoning and say which one is correct. And it looks like this swap and synthesize protocol actually performs much better in terms of self-consistency. Okay, so far I've been talking about like evaluation protocols, not models. Now the question becomes, okay, if you want to use just an LLM, like which LLM works better with what protocol? So it turns out that it's not very consistent. Like the protocol to use is different. Like the best protocol can be different for each model and each data set. But if you optimize per data set, you can actually get pretty high accuracy scores. For example, like for Llama model 405B on this data set, swap and synthesize is better, but on this other data set, GPT-4 as reference is better protocol. And interestingly, on this other data set, a smaller model, which is like 72 billion parameter, works better than a bigger Llama model. Okay, so now we wanted to also see which model, which open source model is better across all the different protocols. Like if you average like all the protocols, which one works better? And there's a clear gap between Llama 3, 3.1, 405B and the 70B, which is expected like here. And however, like Llama 3.1 is much better than similar sized models. Like if you only consider like models that are about 70B parameters, like Llama 3.1 is much better, like significantly better. So if you want to use a open source model for evaluation, you cannot run, and you have hardware constraints and you cannot run 405B, it looks like 70B is pretty good. It provides very high correlation numbers with human evaluators. And then the next thing is like, it looks like the average performance across different protocols is highly correlated with the performance on base protocols. So if you don't use any of these advanced protocols and just prompt the model to say which one is better, and if that performs very high, then you can get a sense of on average what is the performance if you use different protocols. And the correlation is very high, like it's 0.98. So the next question we wanted to look into is like, for each model, what is the optimal improvement we can get if we choose different protocols? We don't use the simple prompt. It turns out that it's quite varied. So if you look at this table here, I know there's lots of numbers here, but you can only focus on the last column. Yeah, and then here you can see that the range of improvements is quite high for smaller models. Like if you have like 7 billion parameter models, based on which protocol you choose, you could get very like large improvements. However, if you move on to very big models like 70B or 405B models, if you change the protocol and then choose the optimal protocol, you would at most get like about 3 points improvement. It is still significant, but is not as high as like 9 points. This means that the bigger models are less sensitive to choice of prompt. They still perform well, even if like you use a base prompt, you don't use like a more complex evaluation protocol. And this is like another thing of like, if you choose the evaluation protocol and then look into which model it provides the highest improvement, it turns out that it's you get quite different results. Like for example, before I mentioned that prepare on average works the best among all protocols. But if you take the max, it doesn't perform the best. Like the max is like metric cross reference protocol or reference protocol and so on. So it means that there's some variance on like which protocol you use and like basically the combo of the combination of the LLM, the base LLM, and the like the evaluation protocol that you use. And here is the correlation of protocol performance between a group of weaker LLMs and a stronger LLMs. So basically, we divided the LLMs into like a stronger and weaker, and then we looked into the correlation between performance on these. And it looks like the correlation here is not very high. The effectiveness of evaluation protocols substantially vary with the base LLM qualities. And like this further like confirms the previous point that like if you have a smaller models and you're optimizing for cost, maybe you need to use a better protocol, more advanced protocol helps there. But if you have like a lot of budget and you want to use GPT-4, then just use GPT-4 and then don't worry about the prompt or protocol that much. And here we looked at the data set, like the difficulty of the data set, basically, difficulty of instances. And here, is the how many of the models get that instance correct. And usually it's like a trend of like upward that like most of the models get a lot of instances correct, with the exception of this data set, LLM bar adversarial. And this was built in adversarial way that they chose examples that the models were wrong. So here it's kind of expected that it has a different behavior. And finally, we looked into what is the correlation between different data sets. Can you use findings from one data set and just generalize to other data sets? It turns out that for some data sets, that might be the case. For example, MT relates well with natural instructions, but not as well with other data sets. And one of the data sets, the adversarial one, actually has pretty low correlation with other data sets. So what are the takeaways? I know I throw you a lot of like findings here and like a lot of numbers, but the main points is that like these LLMs and these evaluation protocols have like biases. Like each of them have a strengths and weaknesses in terms of like their effectiveness. And if you just use a simple base prompt, it tells us a lot. So we don't need to necessarily perform a lot of like complex evaluations to decide which evaluation is better. So if you have a new model and you want to decide if you want to use that or other models, you can maybe just use the base prompt to compare and then go and like build on top of that. And the protocol effectiveness really depends significantly on the base LLMs. You see that like weaker models benefit more from advanced protocols rather than the compared with the more capable models. And different meta-evaluation data sets can exhibit varying difficulty levels and can lead to inconsistent evaluation results. So yeah, this shows that like this type of meta-evaluation is still a challenge because you cannot get like consistently consistent result across different data sets. And in general, this framework that we presented allows us to select an LLM and evaluation protocol combination that provides a good trade-off between the evaluation costs and the reliability of evaluation. So yeah, the work is on archive now, and like we released the code, data set, and everything. So if you're interested in this stuff, I encourage you to check this out. And finally, thank you for your time and for your attention. And I wanted to thank my students and collaborators on these two projects.
Okay. I have a question like in very beginning of your slide, like so you say for model when you have two output, right? For like a very basic model, you don't do any like evaluation selection. So in the beginning, you said when you have two output, but the model will always like prefer the second output. Do you know is there an explanation for this kind of behavior?
Yeah, so this is the behavior that like a lot of work that like on LLM as evaluators have observed. We don't really know why these biases exist. There's a chance that it's related to the training data that these models are trained on. There's a chance that it's because of the training objective. This was a bigger issue in like earlier models, for example, GPT-4 and like GPT 3.5. It's a little better on newer models. There's a still bias, but yeah, these issues exist. Because like the data that they use for training these models is not publicly discussed. We don't know what is causing these biases.
I see. Okay.
Just a quick follow-up question to that. Also really interesting talk. I was just wondering, so have you noticed on, on the similar theme you were talking about how protocol, the effectiveness of protocol depends a lot on the size of the LLMs. Have you noticed this bias with output 1 and output 2? Did you guys test if this differs on like open source LLMs, and does it vary with model size and number of parameters?
Yeah, that's a good question. I think we have some results on that based on consistency. Yeah, this. So yeah, this is averaged over like all the models. Like this is the protocol, and so the higher number means that the model has less position bias, is more consistent. This table basically shows that like if you swap the output, how many times the model's prediction changes, and this is average across all models. So this tells you about the protocol. It doesn't tell you about a specific model size, but we have those results in a fine-grained setting, so it would be easy to compute that.
I see. Thank you.
Yeah, thanks.
I have a couple of questions. When you spoke about summarization of papers, I wonder if first of all, people try to do analysis separately to very high quality documents versus documents, something that you get from maybe your students that are not trained yet, and there is a very little context in the document. So if you try to summarize it, probably you don't expect to get a good summary, right? If you compress noise, you still have some random subset of noise. So that's one thing. So like taking Wikipedia probably will give you completely different viewpoint of what you're doing. And I don't know if people try to do that. And the other question is whether people try to use methods that are trying to understand concepts in the documents and see whether those concepts or the frequency of those concepts appear also in the summary. Like there were in the past some, I don't know how effective they were, latent Dirichlet allocation methods and things of that sort. So I don't know if these kind of approaches are being tested for the quality of summarization.
Yeah, that's a good point. In general, like evaluation of summarization is like still like a problem that people actively look into. There were some previous work, like for example, this auto ACU thing, that like they identify this atomic content unit that basically tries to capture the concepts, the main concepts of the summary, and then checks if the candidate summary like includes these or not. And then they assign a score based on that. So there are approaches like this. However, it looks like now that you have LLMs, you can just ask the LLM which model captures the main content of the document better, and it performs pretty good, even better than this type of auto ACU methods. So yeah, and I do believe that the problem exists. I'm not saying that LLMs solve it, but it looks like LLMs outperform the prior work on this task.
Okay.
Thanks.
And as for the first question, in terms of comparing high quality documents to something that is less.
So if I understood, so the question is like, how would the results change if you use like lower quality document or?
Yeah, versus very high. Let's say you take books. Let's assume that books are pretty good, and you compare it to some papers in low tier type of a journal. Where is it easy for these models and how they compare on a good quality versus bad quality document?
Yeah, that's a very interesting question. We didn't study that, and I don't remember if there are works that actually studied that. What we focused on in this second work was very high quality data sets because we wanted to have high correlation with human, and we chose these data sets because like the agreement rate between human annotators were high. But I do agree, like if you have like data that like is like kind of varied quality, you might get different results. We didn't study that, and I haven't seen any work that studies that. It's very interesting. Thanks.
Okay. So if we don't have any question, let's thank our speaker again. And thank you for joining us today. See you next week.
Thanks
Yeah.
for having me. My pleasure.
Thank you so much.
Bye.
Bye.